Hi, everyone. I'm Aryeh. I'm an open source developer at OpenZeppelin, and I'm one of the core contributors to the ERC 7984 standard. So we'll do a bit of a deep dive today. So here's our agenda. We're going to start with a bit of an overview on the technical, on the technical aspect of how coprocessors work. So we'll be able to, understand the decisions that we made with 7984 a little bit better. So without further ado. So what is ERC 7984, the confidential token standard? It is like a fungible token similar to ERC 20. It enables confidential on-chain token transfers, and something that is a little different here is addresses are not stealth. Addresses remain public, but balances and transfer amounts remain private. Okay, so how does this work? ERC 20, ERC 721, ERC 1155, other tokens that we know and love all agree upon value representation. They agree upon operations, right? But here we're different. ERC 7984 disagrees. So you can have arbitrary methods of representing value and arbitrary methods of actually operating on these values. And I'll demonstrate what I'm talking about over here. So what we know and love, a uint, which is what we use always in Solidity. This is 100 in hexadecimal representation, and encrypted integer below it. That's how we would represent 100. So what does that mean? I don't know. And further, so if we want to do addition with uints, we have 100 plus 100 equals 200 in hexadecimal. But if we have encrypted integers, what do? I don't know. I can add them bitwise, but that's definitely not the answer. So what are these values? These are handles. They're pointers to off-chain data generally, but it's basically data that's stored somewhere else. Where is it? That's implementation specific. Every project can handle it differently, right? Inco has TEs, Zama has FHE, and any other confidential solution could work here. So what is a handle? A handle is 32 bytes. 21 bytes of entropy, which depending on where it's coming from will be different. But in an example of on-chain operation, it would be the operation, the left-hand side, the right-hand side, Boolean, if it's the right-hand side is a scalar, the ACL address, and the chain ID. So, just entropy. Then we have the index, which is the index within an input proof. So sometimes we'll have input proofs. We'll get back to what that is later. But which index the handle came from. If it's not from an input, then it would be 0xFF. Then we have the 8-byte chain ID, we have the type, and the version. So what can we do with this? Really not much on our own, right? You see entropy. What can you do with entropy? Not much. We can't do branching. We can't revert. We can't do native operations. So this is quite restrictive on how we write Solidity using entropies. What we can do is we can use coprocessor operations. So we basically emit events using libraries provided by Inco, Zama, whoever, and those will interact with the coprocessor, and the coprocessor will actually handle these events off-chain. And then we can also do decryption, but decryption has to be asynchronous. Why? Because the data is held off-chain. So you request the decryption, and it will come back on-chain at a later point in time. Very, very rough overview on what we can do with Solidity on a coprocessor. So now that we have some background on that, we'll dive into ERC 7984. ERC 7984 defines 3 events. We have the transfer event, which again, we have the from, we have the to, which are both not encrypted at all. So again, you can see where the tokens are coming from, you can see where they're going to, but the amount is bytes 32, and that is really anything. Right, we allow implementation to redefine what that is. So generally an off-chain pointer, and that amount could be a ciphertext anywhere. Another caveat, why do we almost always store the ciphertext off-chain? That's because the ciphertexts are much, much larger than bytes 32. So for example, in FHE, you're talking about kilobytes. So that's not feasible to store on-chain. And then sometimes the privacy scheme requires you to store these ciphertext off-chain. Then we have the operator. So The operator is how we do approvals with ERC 7984. We actually opted to not do amount-based approvals. We opted to do address-based approvals, which are bounded by a timestamp. And we'll get to why we did that in a moment here. And then we have a method for disclosing a confidential value. So if a user wants to, say, prove that they sent 100 USDC to someone, or they want to display some act that they've done, they have the ability to disclose any handle and show the plain text amount. Again, this is implementation specific, how this works per chain. But this is a core feature of the ERC. So back to what I was saying about approvals. The two functions that we define in the interface are if someone is an operator, and you can you give a holder, and you get the spender and get a Boolean, right? So no encryption here. And you can set an operator. Again, no encryption, no privacy around it. So why did we do that? Let's first look at what other ERCs do. So ERC 20, for example, the fungible token that we know and love and have been using for many, many years, has just approve. Approve is amount-based. ERC 1155 is a semi-fungible token, which is quite old as well. And this is just operator, basically, no amounts. 721 is kind of a mix of the two. So this is a non-fungible token standard, which NFTs we used to use back in the day in 2020 and 2021. You can approve based on the specific token ID, or you can set approval for all. 6909, which is an evolution of 1155, another multi-token, semi-fungible token standard, has, again, both approve and set operator. So you can set based on specific amounts, or you can give all your approval to one infinite approval. So again, we're back to just setting operator. So why did we make this decision? There's quite a few reasons, but what it really comes down to is simplicity and usability. Right? Again, we said we can't do branching, right? So if we have no branching, that means if you have a confidential approval amount, you have to do the entire operation every single time. You can't revert based on, oh, I'm trying to transfer someone's tokens, but I don't have approval for that. And then we would have to write another storage slot every single time. And then again, debugging what would happen there is quite a bit more complicated, because now you have another matrix of what could have gone wrong, meaning could have been lack of approval, could have been insufficient token amount, could have been overflow summer. So we opted to just have unencrypted allowances, and it's simplified the process quite a bit. Finally, we found that through looking into historical approvals on ERC20, the far majority of ERC20 approvals were for either the max amount or the full token balance. So here we actually are adding another level of security by having this allowance be time-bound instead. Okay, so let's get up to the next function. So we have the transfer function. The transfer function always specifies where it's going to and the amount that you're transferring in the form of a handle, pointer. Again, implementation specific. But we actually specify 8 transfer functions, which are all of these. And why do we have 8 transfer functions? It's a good question. So we have all the different permutations of whether or not you're transferring from. And so, right, transfer from is utilizing that operator. You can transfer on behalf of someone else. So say you're a lending platform and the user approves you to transfer their tokens for them. You can call transfer from your user to your contract and get their tokens. Input proofs, which I promised to get back to earlier. So input proofs prove that you know the value of an input. Again, this depends on what type of method you're using, what provider you're using. This can actually be any additional data that's necessary when you're taking encrypted value from off-chain to on-chain. In the Zama solution specifically, we need an input proof to prove that you know the value of what you're passing this handle. And why is that? Because if you're bringing a new value on-chain, we actually kind of reveal some information about that, right? So if you transfer your balance from your balance to someone else, so say Alice has X tokens, Bob has Y tokens, and you have Z. If you take your tokens and you transfer B tokens, for example, right, Bob's balance, and you see that it's successful, you can see, oh, I have more tokens than Bob. But even further, you can actually see the diff between before and after, and that would reveal Bob's balance. So that's why input proofs are so important, and we require them if you bring a value from off-chain on-chain. Third, we have callbacks. So this is like 1155, ERC 721 have optional callbacks. Actually, 1155 has mandatory callbacks, but we have optional callbacks. So that means, right, even with 7702, not all wallets have this the batching functionality, which we are starting to come to have roughly everywhere, but still not yet. So callbacks allow you to, instead of approve and then call, you can directly call a contract with a callback. So you transfer tokens with a callback, and after the transfer, it calls the contract to notify the contract that it got the tokens. So the contract has the ability to reject the tokens. The contract has the ability to operate on the amount, and if the amount is not sufficient for what it's trying to do, it can return a false boolean, and the tokens would be sent back automatically. So there's a bunch of different options the contract has to do if there is a callback, and it can operate on that. So if a user wants to buy an item, it can call a contract with a callback, and maybe they're getting an NFT or something. Then we have quite a few more functions, but these are relatively standard. We have the name, the symbol, the decimals, all straight from ERC20. We have the contract URI, which we've seen from the NFT age that people really like associating data with their tokens. So this allows users, developers, to associate metadata with their confidential tokens. The total supply and the balance of each user. Again, total supply and the balance of the user, returning these ciphertexts implementation specific. We've been working on the 7984 standard for quite a while. This is an old mock-up version, but Wizard, if you've never used it, allows you to take different contracts from the Open7 libraries and use some permutations and really easily deploy them. The confidential 7984 token is almost ready for use. When Zama is on mainnet, you'll be able to really easily use Wizard to deploy the tokens, and this is coming soon. Some other features that we at Open7 have built on top of 7984, a bunch of extensions. We have the ERC20 wrapper extension, the freezable extension, observer access, which is good for custodians to be able to see what's going on. So if you have some sort of regulatory reason that you need to be able to see it specifically with your given organization EOA, you can do that. We have omnibus extension, restricted votes, RWA. Please take a look in our repo. These are all coming out in our next release of the confidential contracts, which is this week or next week. And finally, there's a question of why do we have this standard? If there's so much that's implementation specific, basically every single time that we saw a confidential value, it's implementation specific, right? Every contract can interpret value, interpret operations differently. So how does this standard actually help us? That's a good question. But the answer is we can start always with a shared interface, a shared set of contracts. And it's kind of like deploying to a different EVM chain. So these contracts aren't really able to interact with each other by default, meaning if you're on a different chain, you can't call a contract on another chain with a lot of bridging infrastructure. But right, you can build a contract for Arbitrum and you can easily deploy it on Ethereum if you decide later. So we're working to make sure that when you develop for one confidential provider, it works really, really well, really easily with another confidential provider without a lot of work. Thank you. If you're interested, please look at our confidential contracts repo. If you have any feedback on ERC 7984, it's very much in draft phase still. So please do hop on Ethereum Magicians or leave a comment in the GitHub repo on any feature requests or issues with 7984.